So our next speaker is Elisabeth, and again, now we're sort of still on the theme of sounders, but switching from narrowband to high spectral resolution detection and retrieval of cloud properties.
Yeah, thanks. Yeah, I jump right in. These are our current operational sounders in orbit. There's on Alpha, Yasin on November 3, and that will be the Chris on Zoe. So the spatial resolution of all the sounders is about 30 kilometers in radius, so that's much higher than temperature. But the spectral resolution is really high. So the radiance is measured in the spectral range from 3.6 to 15.5 microns using several thousands of channels. And we will see later that this high spectral resolution translates then to high vertical resolution temperature water vapor profile, and also allows the retrievals of accurate retrievals of cloud parameters and surface parameters. What I love about hyperspectral instruments or hyperspectral measurements is that if you look at the spectrum, you can see quite a bit already about them. So on top, for example, I have CIMSS spectra, and usually cloud spectra can be easily distinguished from clear ones. We all know that the brightness temperature in the vapor region corresponds roughly to the surface temperature. So we have the clear spectrum, that's the dark red one, and then the low-level water clouds, they look very similar to those, but just the window temperature is a little bit lower. And then the ice clouds are really nice too. They have this nice slope in the vapor region, and this is due to the certain characteristics of the refractive index of ice particles. And then we also have clouds. Look at the lowest two spectra, the blue ones. So these are now high, really optically thick clouds, where all the levels from below are attenuated, so they don't reach the instruments, and only the levels above the cloud top, so these are now the stratospheric levels, they all have warmer temperatures than the cloud top itself. That's why, for example, the ozone band is sticking up. And here I also show it as a couple of spectra and the full granule of the acid spectrum. So we have the entire range of 30 optical peak to clear skies. So from the previous slide, we already see that there's a lot of information contained in infrared spectra about cloud properties. We can also look at sensitivities to certain cloud parameters. So this is, for example, sensitivity to cloud pressure or cloud altitude. And I'm separating here ice clouds and water clouds. These are simulated brightness temperatures for different cloud pressures. The right smaller images show the long-wave CO2 absorption temp in a little more detail. So what we can see, for example, that low clouds, look at the water cloud panel, the low clouds, it's really difficult to distinguish those from clear skies. And the same is now true for clouds with very low optical depth. So that is now the sensitivity to optical thickness. Again, low clouds and optical thin clouds are difficult to retrieve. So it's much more challenging to get the cloud from pressure, the cloud from height. And sometimes it's just not possible in the infrared. So we retrieve the cloud parameters now simultaneously with the others. So with the other parameters like the profiles and like the surface parameters, we use our dual regression retrieval algorithm. But I want to say here that it's not just a simple regression algorithm. It's because we add a lot of additional steps to account for the nonlinear dependency of spectral radiance on cloud top pressure and also on atmospheric moisture. So it's more a physical statistical regression approach. And the details can be found in one of these papers. I just want to emphasize here that the cloud pressure comes now, or we derive the cloud pressure directly from the temperature profiles, not just from a few selected channels. So these are our cloud parameters now for one case. That's a low pressure system over the Alaska Gulf. So we have cloud top pressure, we have the cloud optical thickness, cloud top temperature, measure effective cloud emissivity and obviously we also have the cloud mass. I'm comparing this now with the Weisz image and the infrared channel. We see the nice details in the Weisz imagery, but this is CIMSS now. We see that all these spatial features are also detected nicely by CIMSS. And now, at the same time, we can add real quantitative values to the scene. And that's why we believe that if we add hyperspectral sound and retrieval products to portrait imagery and data, that we have the potential to improve, for example, forecasting capabilities. We also provide a measure of uncertainty and accuracy to our retrievals. This before under certain situations, it is very difficult to distinguish between clear sky and cloud, especially if the clouds are low or if the clouds are very thin. So for these scenes, that happens very often in cloud edges. We assign the clear cloud detection as uncertain, and then we also, since our cloud temperature depends on the temperature profile, we also provide an overall tropospheric error with respect to a model atmosphere, to a model profile that's shown on the right here. We can also derive other products from our standard products, for example, time densities or time differences. We can show it as an absolute difference, like the one on top. So between two overpasses of the same instrument, if you want, or also of different instruments, like this is now ERC cloud pressure, CIMSS minus ERC cloud pressure. Or we can also compute the change per hour in cloud pressure, again between two overpasses. So we have CIMSS with ERC on method A, CIMSS with ERC on method B, and ERC and CIMSS. This is now for our more Oklahoma tornado case study. We also studied Hurricane Sandy. Again, our cloud pressure retrievers compare really well with what we can see from the imager. So we have CIMSS and Weisz and ERC and MODIS. This is now a cross-section to the same scene. So you can see Sandy and then the low-level cumulus over the ocean, and then the tropospheric, the tropical high deep convective clouds. So we see that the hyperspectral sounder retrieval product compares really well with the LiDAR. So that's Calliope on Calypso, which, since it operates in the optical and not in the infrared, has much more sensitive to really small particles, so it's therefore very sensitive to high pixels and antennas count. I don't know how to do that. Oops. Okay, sorry about that. Okay, so that's this is now a table showing also Calypso, comparison with Calypso. Shows now the bias and the standard deviation of imager alone, the sounder alone, and an merged imager and sounder product with respect to Calliope for different cloud scenes. So this is from this paper here. So what we can see from here that overall that the hyperspectral sounder has the lowest error, so it compares best with the LiDAR. What we also can see is that if we work with both the imager and the sounder together, so we make use of this high spatial resolution of the sounder and the high spectral resolution of the imager, we can also improve the results over the imager alone. So up to now, I showed you results which were derived from live broadcast or real-time data. With that, I hope I demonstrated that our retrieval system is capable to give you a fast, accurate picture of the atmosphere. But since the retrieval system is very efficient, we can also do global and long-term analysis. So today I'm going to show you cloud frequency and cloud pressure retrieved from 10 years of EASI, 10 years of EAS, and I also have one slide showing 6 years of EASI measurements. We have processed 4 months per year per instrument so far. So we are using the space-time threading approach, Nadia is describing in this paper down here. So we snap the data to a global uniform 1 degree centigrade, then we calculate daily means for each cell, and from the daily means we calculate the number of means. And that's what you can see here. Now that's the EAS, February and August, low clouds and high clouds, cloud pressure. That's the average over the 10 years, 2003 to 2012. As expected, we find the highest clouds in the ITCC, and we also see nicely how the ITCC moves from February for boreal winter. It moves north in boreal summer. It also expands over Southeast Asia. The white spots on the lower image now refer to regions where we don't have a lot of high clouds. So these are the subtropical deserts, these are the subtropical high oceans where marine stratus are prevalent. So now these are now the corresponding cloud frequency for the same time period. Again, the highest clouds are found in the tropical ITCC, and far less frequent high clouds are found in the subtropical oceans, as you can see on the west coast of Africa and South America. Now, this slide shows now 20 years of Earth observations and 10 years of Earth observations of high cloud cover. So there are obviously some differences, not only the spatial resolution, but we have to account for the differences in spectral resolution. Then we use different retrieval and filtering techniques. The time period is not the same, the time length is not the same, but I think it's very encouraging that we find the same spatial features. So this is now the overall, the globally, so near global average cloud frequency for these 10 years. And from that we can see that clouds are found in roughly 80% of the Earth observations, and high clouds are found in roughly 40% of the Earth observations. The same figure now for the tropics. We have about 75% of clouds and 40% of high clouds. And here we have the seasonal change is much stronger here now compared to the previous slide where we saw the global image. So we have more high clouds in February than we had in August. So this trend now, the previous trend now compares well with HERS, what HERS found. And HERS finds more tropospheric high clouds than is the International Satellite Cloud Climatology Project. I also want to mention here that we saw that we have slightly more high clouds here in Earth than we find in Earth, and that's mostly can be explained that the hyperspectral sounder, if you use the entire spectral range or most of the channels, then you have an improved capability of detecting high and thin optical clouds compared to a full-spectral image, for example. We can also look at the deviation from the overall mean. So that's now again just for the tropics. We see that the average anomaly in high cloud frequency from Earth is about 0, with the standard deviation less than 1%. Below I'm showing here MODIS, which sees a slight trend from 2002 to about decreasing trend to about 2004. Then it stays fairly constant. The values are somehow comparable to what we find on Earth. This is now just an example of a 2012 cloud to pressure and the cloud frequency anomaly. So that's the difference to the overall 10-year mean. This needs to be studied in more detail, but you can see, for example, that over the Central Pacific or over Southern Europe, you see a decrease in cloud altitude, and you can also see that this relates to a decrease in cloud frequency over the same frequency. So finally, this is EASI now. I only have one slide here, so that's EASI. In EASI, 6 years of high cloud in cloud to pressure and in frequency. So they look similar. Remember, we use the same retrieval algorithm, also the same threading algorithm, but there are differences, and we are currently studying these differences to understand where they're coming from. So a lot of them are probably caused by the different orbit times. So we have an afternoon and a morning orbit, but also there are other differences might be caused by the differences in the instrumentations. Yeah, so that's my summary. So what are our strengths? We have a multi-instrument retrieval approach. It is publicly available. Has been proved to be fast, efficient, accurate. I also want to mention that it's really easy to adapt this retrieval system to other hyperspectral sounders or to future hyperspectral sounders, either if they're on satellite or on an aircraft. And if they're on a satellite, it doesn't matter if they're on a geostationary orbit or on a polar orbit. The retrieval system works on real-time data, so you can do storm analysis. It works also on archive data to do climate trend studies. We retrieve the parameters simultaneously, so we get a complete instant picture of the atmosphere, so that's very important too. And we have shown that the improved vertical resolution in soundings also yields in a better capability to make tight optical fields in clouds. What are our weaknesses? So we have limited capability to detect optically thin or very low clouds, and this is mainly due to the operating range. So we are in the infrared, so that is just true for all the infrared instrumentation. And due to our relatively large footprint size, it's possible that we miss some clouds or small horizontal extent. So we don't retrieve a lot of a couple of cloud parameters, certain cloud parameters yet, but we will consider. And since it's a global retrieval scheme, so it occasionally happens that profiles at a small local scale have less accuracy. But I want to mention here too that it is possible to make the retrieval system more locally, and that's what we plan to do for a geostationary sound. Regarding symmetry, so we're already processing multiple instruments and we're continuously doing intercomparisons. We saw that hyperspectral sound retrievers add quantitative values to and therefore complement visible infrared imagery. We did some work on merging the imager and the sounder data to improve the imager cloud height retrievals. And with the cloud climate work we did so far, we are working towards a